Welcome to today's robotics seminar. Today I'd like to introduce an old friend of the Robotics Institute. He was a research scientist here about a decade ago. And since then he's gone off to the University of Maryland and is now basically starting his own Robotics Institute, the Robotic Center at the University of Maryland. And he's acquired all kinds of accolades. It's basically, I can't even barely keep up with all his great achievements. So today he's going to tell us about both his own research and a little bit of an idea of what's going on in his own department. And knowing SK, he's going to try and integrate it all into one story. I don't know how he's going to do that, but I'm quite anxious to see. So it's my great pleasure to introduce my friend, Professor SK Gupta.
Thank you, David. Okay, so what I'm going to talk to you today is going to be about how you use simulation to do computational synthesis. And particularly, I'm going to mainly talk about the kind of synthesis problems that arise in the robotics field. So we will take a look at some examples from behavior synthesis as well as robot physical structure synthesis. So that's what I'm going to try to do. So before we get into the technical presentation, let me give you a quick overview of new Robotic Center, which we have created at University of Maryland. So the center started in March 2010. It has basically consists of 18 different labs which work on different facets of robotics, which go all the way from mechanical engineering aspect of building robot to building very small robot to building nano robots to the vision and computer science. So we span a wide variety of things, and many of these labs are also application focused. So some labs are focused on medical robotics, some labs are focused on space robotics, some labs are focused on unmanned vehicles. So we have a whole spectrum of activities. And we have about 25 faculty members which come from 7 different academic disciplines under the center doing different facets of robotics. And the current thrust in the center are 5 different thrust areas. So the first thrust is basically where we're looking at cooperative, collaborative network robotics, where lots of robots working together to solve a complex problem. Then we have a thrust on unmanned vehicles, so where we build a lot of different unmanned platforms to do a wide variety of search, rescue, recovery, reconnaissance type of problems. Then there's a major thrust in miniature robots, where we are trying to make very small robots, as well as basically trying to build robots which can manipulate very small things. So that's another important thrust area. Fourth one is in the medical robotics area. There we are looking at into all kind of surgical robotics applications, as well as other drug delivery, therapeutic rehabilitation applications. And the final one is in the robotics in extreme environment, where we are looking into space robotics application and deep underwater robotics application. So that's kind of gives you coverage of center. So let me quickly tell you what my interests are. So my interests are basically nowadays in simulation-based computational synthesis, and I like to explore problems from design automation, where people are interested in solving some design automation problem. They may or may not be robotics in nature. Manufacturing automation, once again, those problems may or may not be robotics in nature, and a lot of things from robotics. So that's what I'm mainly interested in. So let me explain it to you what this field is all about. So traditionally, the way people use robotic simulation is the following way. So you know, somebody sits down, comes up with a solution, and then you can use simulation to evaluate it, how good this solution is. Is it good? Is there any problems with it? And if you have parameterized your solution, then you can use simulation to also do optimization. So you can basically say, okay, I'm going to start tweaking parameters and then try to optimize whatever initial solution I have proposed. So that's a traditional way people have been using simulation in the field of overall design, whether they're designing robot or mechanical structures or some other thing. So that's the traditional view of using simulation. Now, emerging role of simulation is that can you really use simulation to invent things? So the idea behind that is that we don't want to basically feed an initial solution and then simulation just optimize it and tell us whether this is a good solution or not. Can you really use simulation to basically invent something new? Or how can you do that? Now, there are two different research communities. So one community is automated synthesis community, and this community has traditionally solved lots of problems where decomposition works very well, physical principles are reasonably well known, things can compute very fast, so VLSI design, other logical construct, so those people can quickly synthesize it, and they would say, you give me the problem, I'll compile it into a solution. So that's very well-established community, and they have lots of suites of technique which they use. On the other hand, you have a simulation community which takes great pride in building highly accurate, high-fidelity simulation, which then can actually simulate all kind of physical effects and tell you whether something is working or not, right? So one way to think about solving the problem is that if you can connect automated synthesis tool with basically these high-fidelity simulation. If you can connect, then automated synthesis tool would basically create new solutions for you, and simulation would evaluate them. And if you can actually get these two things talking to each other at the right bandwidth, then hopefully you can create lots of new things. The challenge arises because simulation traditionally, or at least the physics-based simulations traditionally are very, very slow. So they're accurate, but they tend to be very slow. So on the other hand, when you take a look at automated synthesis community, they've been working mostly on the problems where problems can be easily decomposed. So you can easily decompose it, and then you can go ahead and solve decomposed versions of things and then put things together. But many of the problems that I'm going to discuss today, a nice decomposition doesn't really work very well. Things are all coupled. I mean, all kind of complications happen. If you add a little feature over here, it creates a chain reaction of causing lots of problems. So you need to fix that area too. So basically, it turns out that you cannot simply take existing high-fidelity simulations and existing automated synthesis tools and glue them together. It doesn't work that way. So you have to really enhance things both sides. So what my research program is all about, enhancing these things from both sides. And we usually look into cyber-physical systems type of problems where things cannot be easily decomposed. If you can easily decompose things, then you wouldn't need the kind of things that I'm interested in actually working on. So our research is basically, from one side, extend the automated synthesis technique, and from the other side, extending basically the simulation technique. So that's what most of the time we work on. And the way I usually work is that I will get involved in some challenging application, and we will use this framework to think about it, and then we are really interested in solving the problem arising in that application, and hopefully whatever we learn from that application informs the framework, and the next time we get involved with some other challenging application, we can reuse that knowledge. So that's how kind of we think about it. So quickly talk about what kind of enhancements are needed in simulation. So imagine a problem that you are given a problem where you need to synthesize a robot behavior which has to be reactive in nature, and this robot boat has to operate in a high sea state, and it's fending off some other boat, right? So if you think about simulation, and everything matters, the way boat moves, the ocean state, lots of different things matter. So if you think about basically simulating ocean and boat interaction, I mean, that's very slow. It's going to take you very long. And why you care about this? Because you need to really know exactly what kind of turning radius you're going to be able to acquire in a particular setting, how fast you can accelerate, because otherwise this guy is going to, get past you. So all those things are important, and you need to know them fairly well. Now, if you think about traditional problem where people have been exploring simulating boat in the ocean, I mean, it's very, very slow. I mean, for some of the problem, you may be able to simulate few seconds of operation of the boat in few hours or few days, depending upon what physics you're modeling. So what kind of technique I'm talking about? So in that case, you really can't use that for synthesis. It's just not going to work. So you need to think about doing some model simplification. So model simplification is that when you take a look at the model of the boat, not every detail in the boat is important. So you can actually start losing some details on the boat. Yeah, of course, your physics deteriorate a little bit, but if you can live with that inaccuracy, you're in fine shape. Order reduction. So for example, if the boat is not going very fast, maybe hydrodynamic force which are coming because of planing effect, you can drop them. Those are not that important to you. And then meta modeling. So idea is that can you have a computer cluster on which you can run this thing over 15 days and collects lots of data, and then during synthesis process just kind of interpolate over that data. So that's kind of meta modeling approaches. So these are the three things that we need to do, but we want to do that automatically. So a lot of work that you're going to see, all this will be, incorporated in it. Now, when we think about the automated synthesis problem, and when you are thinking about problems which are not easy to decompose, so in that case, you need some extension in that area too. So what kind of extension we are talking about? So ordinarily, if you have a complex problem, you need sophisticated solution. So if you're going to synthesize a sophisticated solution, a problem which is not amenable to decomposition, you have to, basically use some evolutionary technique to synthesize pieces of it. Then you have to use some kind of reasoning technique to figure it out what little piece need to be synthesized. So all of that needs to take place in order for you to be able to synthesize anything which is sophisticated, and I'll talk about that in a minute. Then what happens is that if you have a large search space, if you discover a principle which is telling you this portion of the search space is not going to work, you have to do aggressive pruning and caching and all of those things for that. So we have to incorporate those. Because in that case, simulation is still slow. So you cannot simply say that, okay, so what? We'll just keep evaluating the things, right? So that idea doesn't work. And then effective evaluation function. So many of these problems will have characteristic where you will have an overall score, but remember, overall score doesn't help you actually do the synthesis process. So you need to have lots of surrogate functions that are needed to guide your overall synthesis process. And finally, representation. Because whether you're going to be successful or fail will ultimately depend upon whether you have the right representation or not, right? So these are the kinds of issues that we work on when we take a look at basically the automated synthesis aspect of it. So this is the framework by which we kind of think about all these problems. So first layer is just somebody giving the requirements, and the second layer is basically the automated synthesis, and it has now been augmented by all different things that I said, which includes this whole idea about combining evolutionary technique with the reasoning technique to synthesize sophisticated solution. It includes search space management, and then designs, of representation, design of evaluation function all goes in there. And then you have these simulators, which you bring in model reduction, model simplification, and meta model. So that's how you kind of put the whole pieces together. And of course, I want to point out that humans play a big role in all aspects of it. So we are not trying to get human out of the loop, right? Human just focus their energy on interesting things. They don't do grunt work. That's the point, right? So human play a big role in defining the requirement. Human play a big role basically sometimes even seeding the initial solution or the starting solution from which you go. And humans play a big role in guiding the meta model development, model simplification, model reduction process, right? Okay. So that's how we think about it. So that was big abstract thinking. So now let's dig deeper and try to see if we can look into three challenging problems and then try to see how all this is going to work out in that one. So the first problem that we are interested in solving is basically the following problem. You have a boat which needs to defend a target which is being attacked by some other human-driven or autonomous boat, and you might be operating in wide variety of sea states, and you cannot afford to do very detailed planning, so it has to be fairly reactive behavior. You can do very short-term planning because you have to react very, very quickly. This work is funded by Office of Naval Research, and a large number of people work on this team. So, and this work we are doing for this unmanned sea surface vehicle high to force version of it. And we are mainly focused on the blocking task, right? So we are interested in synthesizing the blocking behavior, right? Okay. So overall scenario roughly goes like the following. In the middle, you have some protective object. USSV is patrolling around it and making sure that no intruder is trying to come close to it and cause any damage to it. So you draw two zones. The first zone is danger zone. So if anything enters the danger zone, you actively block it. So you go in front of it and kind of slow down its advancement towards this target. And there's a buffer zone. So if anything is outside buffer zone, you don't care. But if anything enters in the buffer zone, you first go and just give them a warning, get out of there. And if they don't listen to you, then you actively block. So that's what basically this mission is all about. Okay? So that's what the goal is. So this is a problem fairly challenging from synthesis point of view, because you need to kind of really know all your capabilities in different states. What turning radius you can get, what acceleration you can get. Of course, there's uncertainty in the world. Adversary could be using all kind of tricks on you to try to get past you. And you are going to have all kind of physical limitations of when you brake. It's going to take you some time to get there. So all sorts of things which make the problem difficult. And you have to find the right balance, because other goal in this case is not to blow yourself up by just directly striking into the things. I mean, that's a requirement given to us by our ONR program manager, right? So we can't be synthesizing that behavior. So it's a challenging synthesis problem. So if you try to write a code for, and then I'll tell you a little bit later. So if you try to write a code for it, it's a fairly challenging problem if you write a code for it and you try to solve it, right? And it takes significant time and effort to write code for it. So we said, okay, here's our overall approach. Once again, we begin with a simulation model where we can simulate these USSVs in sea states, from which we build the meta models, which basically under different sea states give you what turning radius you can get, what the uncertainty is going to be depending upon the kind of controller that you're running on USSV and your position and the velocity, what your acceleration is going to be under different conditions. So you generate all that meta model, right, which you're going to use in the real time and you're going through it. And then we have this virtual environment in which you can actually go ahead and play a game. So you can put a head-mounted display, go inside the virtual environment, drive this boat, right, if you wanted to. And then you can actually synthesize policy. So computer can synthesize policy, human can synthesize policy, you can play a game against each other, you can play a game against human. So you can do all sorts of different things in that setup. So we have built that. So first challenge is basically getting the model to work at interactive rates. So the first problem is that if you are given an ocean state and you're trying to figure it out how boat is going to go through it, and if you just do displacement physics. So one of the things that we said that planing physics we're going to ignore because our boat is not going to move very fast. And when our program manager said it's okay for now for you to make that assumption. So we went with that. So then what happens is that if you just integrate the known equations over the entire boat, it turns out that, so in order to maintain interactive operation, you want to get 20 hertz at least so that people can play this game. But if you just integrate the equations over this entire boat surface, I mean, this is horribly bad, I mean, in terms of speed. So what you have to first do is that you have to do all kind of simplification. So we began with doing a spatial decomposition where you take the representation of the boat, you start clustering different facets, and you just compute the force and centroid of these facet clusters. And then you exploit temporal coherence because certain times the waves are approaching very slow, so from one time instant to the other time instant, force doesn't change, so you cache the force, so you do all those tricks, and then of course you have parallel implementation. So once you do all of it, then you can actually write a simulator for the boat using displacement physics, which you can drive in an ocean with a wave with a very realistic motion. So it's interactive. So you can now drive it around and you can actually maintain your. So this chart just shows you that what gains you had basically, right? So it turns out that we can actually speed up this thing tremendously. So if you started with the baseline where we were not doing any kind of simplification, one time step, which is in the real time, happened to be 0.07 second. It was taking roughly 1 second to compute. But once you have put all of these things together, then you can actually do this computation in 0.02 seconds. Remember, there are multiple boats in the scene, so it's important to reduce this time down, right? So these are all the different model simplification techniques applied, which then gets you reasonably good simulation speed. Okay? So once you have that, then using which you can build this virtual reality-based simulation environment where people can drive these boats around and kind of do whatever they want, and you can run a lot of games with the different human users and see how they're playing it. Okay? So then we come to the synthesis problem. So in synthesis problem, you basically say, okay, we're going to use genetic programming to synthesize a policy, and policy is going to watch what state we happen to be in, and a state just is encoding where the value of a target is, where the intruder is, what intruder's current speed is, what my current speed is, how we are all oriented, and using that, and what the C state is, then you're going to take certain action, right? So you start with genetic programming. You basically see something very simple, see what happens. Then you run the simulation, and you say, oops, I made a mistake, and here is a state in which things failed. You use that state to seed another genetic program, you synthesize something, and you patch it. So you keep going in this loop as you discover states which are failures are happening, and you keep patching it up, right? Till you get enough sophisticated solution, right? And you keep partitioning state, combining, recombining them, right? So that's how it works. So this is just giving you more details. So what happens is that you are interested in anytime you have a policy synthesized, you execute it, you see where it fails. Once you spot where this thing fails, you actually try to go back a little bit back in time, because the failure actually triggers somewhere back in time. And we try to learn that by running different simulations and using different time parameter and estimation on it. And from that, you try to synthesize another state, and you incorporate in this overall policy. So that's how this whole scheme kind of works. So then the question is how well this idea works. So if you can actually synthesize policy this way versus somebody writes a code, are you going to save anything? So what we did was that we implemented, so here's what we did. We first got a bunch of students in the VR world play a game against each other. So a bunch of people were going to be driving USSV, a bunch of people were going to drive Intruder. We said, okay, play against each other, right? Pairwise combination in VR, and just see how well you do against each other. So now we had some idea about how these people were trying to attack the boat and what kind of time they were getting against these human players and what kind of behavior they were exhibiting. Then we said to one person, you code that thing up, however they were attacking. So he took several weeks to code up this thing, right? Then we said, okay, let's play this human-coded intruder against human players. So it turned out that human-coded intruder, which took us a long time to code, was doing reasonably well against human players. So we said, okay, this is a human competitive intruder. Now we're going to do two things. One, we're going to synthesize a USSV blocking logic using the synthesis process that I just described, and we are going to write this by hand, right? So once again, somebody took a month to write that thing, and we synthesize. And synthesis process takes about a few days on a computer cluster, basically, right? So the question is, how well this machine synthesized code stacks up against this blocking defense written by a human programmer, right? Against the secret intruder. So let me first quickly, actually, let me just tell you the result, and then I'll show you the, okay. So what happens is that, so if you write the human intruder code by hand, and you write a USSV logic by hand, and you play against each other, lots of games, median time that you can delay arrival of this intruder to the target, because you have very little speed advantage. So eventually this intruder is going to reach the target. You can just delay it. 46 seconds. And what happens is that if you start synthesizing things, so you start with generation number 1, where you have synthesized something which is pretty bad. You find out what its weakness is, and you create a patch. So these, on the x-axis, we are showing different patches, right? Roughly after applying 80 different patches, it turns out that synthesized code is exceeding now the performance of the code written by human, right? So now we are approaching where we can actually use the synthesis, which takes few days in a computer cluster to synthesize this logic. And if you basically give it human to synthesize, it takes them 3 weeks, a month. Now, clearly, if humans spend more time, they could write better. But clearly, if you gave computer more generation, perhaps it could do a little bit better as well. So this shows that, using synthesis in kind of challenging problem, we are able to actually synthesize something quite useful. And then, of course, we went back and played with the humans and so on and so forth, and code seemed to work reasonably well. So let me show you a quick. So this is completely, so basically Blue Boat, I believe, is the, in this case, the USSV. Red Boat is the intruder. So this is completely synthesized by the program, and the target is located on the top right-hand side of the screen. So you're seeing that, how the blocking is taking place. And this thing actually, every time it moves, that it's going to try to come. And both of them have been given this penalty function that they cannot crash, because you don't want to lose your USSV ramming into this thing, and this intruder is not interested in killing the USSV. It's interested in going after this valuable target. So that's how kind of this works. And then I don't believe in doing things only in the virtual world. So we always are interested in creating a physical setup and trying these things out there. So we have a nice neutral buoyancy tank at University of Maryland. So we basically set it up. So we got 2 little boats. And basically, in this case, we have a head-mounted camera mounted on the ceiling, which is beaming both people their coordinates, basically, right? That's how they're seeing each other, right? And then you do the same thing. So you run one boat with the logic that you have coded it up, and another boat you let it control basically by the, either a human can drive it or you can run it by the intruder logic, right? So that's how these things kind of work. So we are conducting experiments and trying to see how these things work in the physical world as well. So,
can I ask a question?
Yeah, absolutely.
This is a little bit beyond the scope, probably, but
sure.
In real life,
right.
The state of the sea, which you have mentioned several times, is really a big factor.
Right.
In high seas, the strategies would be totally different. Being able to take advantage of being in the following sea, for example,
yeah, absolutely,
gives you huge advantage.
Absolutely.
And so somehow organizing your orientation relative to the direction of the sea, right, is a major strategy.
Yeah.
And that's in the swimming pool. It's probably not.
No. In the physical test, physical setup, we won't be able to do that thing right now. What our plan is that probably put a wave generator on the end of it. So we, depending upon what kind of wave we can generate, we might be able to at least do some of the things. But the major problem is going to come because of sensor, basically, right? Because we have a sensor which is mounted on the ceiling. So in the ocean, lots of things happen because you basically be blinded because of the big wave ahead of you. Somebody behind that wave can be doing all sorts of things.
And there's in one of the recent pirate instances, the strategy was for the destroyer to circle the pirate and basically swamp the boat with huge waves. Right.
No, we're not doing that strategy. I mean, the idea here was to try to demonstrate if compute. So what was the point of this exercise? The point of this exercise was that a lot of people in ONR were not convinced that you would ever get the simulation to run fast enough to do anything useful in the computational synthesis area. So we wanted to show it to them that you can if you work on simulation and use some of the other things. Because a lot of simulation community in ONR basically take a great pride in creating very accurate models, right? Or very accurate simulation. The second question is basically, can automated synthesis actually really do on such a complex problem? Because if you're going to use evolutionary technique, so if you see classical genetic programming, and if you just use genetic programming without going back and forth between these feature things and automatic detection and what state to create, I mean, you'll be stuck with a performance of about 9 seconds, right? So that would be the limit of state-of-the-art genetic programming if you were not going back and forth between reasoning and genetic programming, right? So that was another thing that, yeah, we know synthesis, we know genetic programming, but genetic programming, the best it can do is, a few seconds, right? So we wanted to demonstrate that we can go over that hump, basically, right, in this case. So to summarize this case study, that we developed a USSV simulation environment, and we showed that actually using the simulation environment, you can synthesize some policies which seem to look promising. And we also showed that actually there are our policies, when you analyze them, they have lots of very complex features, basically, right? So that's what's kind of we managed to show in this case study. Now I'm going to switch gear and work on now physical structure problem. I'll show you how all these ideas work in a physical structure problem. So second problem that we are interested in working on for a while is create basically flapping wing micro air vehicles. So the idea is that these vehicles which are going to fly by flapping their wings, right? Okay. This work is funded by Army Research Office and Army Research Lab, and large number of students once again work on it. Arvind, Wojciech, John, Dominic, and I have a collaborator from ARL, Steve Wilkerson, and Hugh Brook, who is a professor in our department. So why interest in this thing? So fixed wing flight, basically very efficient, it's a lot of speed, but poor maneuverability. You can't really maneuver in a tight space. Rotary wing flight, which is the helicopters, not very efficient, but very good maneuverability. However, there's no good way to suppress the sound being made by these helicopters, because the blades spin at very high RPM, create signature. People would know far, far away that there's a helicopter there, right? So if you want a stealth and maneuverability in a combo, you have to look at the birds, which are, basically they're very quiet, and they're very maneuverable, right? So Army has been interested in basically flapping wing flight for some time, and we got one of the Muries, and they said, hey, why don't you guys start looking into it? So that's how I got involved in it. So in this case, we looked at different aspects of it, what we could work on. So basically, if you think about birds, what are the main functional elements? So functional elements are your electronics. So we said, I'm going to work on it. Actuator technology, when we started on it, basically small motors were the only game in town, and they still appear to be the only game in town because of power consumption, efficiency, and everything. So there's not much we can do there. So there are two areas that left. One was wing design. Another one is basically design of the drive mechanism, right? So today I'm going to talk about design of drive mechanism. Now, design of wings also we have worked quite a bit on it, but design of wings we do it purely experimentally. So that doesn't fit the theme of the talk. The reason is that when you're trying to do these flapping wing flights, aerodynamic calculations are extremely difficult, and you cannot do them with a reasonable accuracy. So we do our wing design basically on a test stand by putting these wings and kind of flapping them and doing all kind of measurements on it. So, but we use a lot of simulation technology to design our drive mechanism. So what is the drive mechanism problem? They take the motion from the motor and impart it to the wing, right? Now, drive mechanism, you want to make it as light as possible because you want these birds to have as much possible payload as can do, right? So why is this problem now challenging? Because now on a drive mechanism structure, you're interested in finding right shape. You are interested in finding right shape parameters. You are interested in, because in this case, we knew that we're going to be using some kind of advanced polymer for making these things. So you have to worry about all kind of molding constraints that are going to be imposed. Because if you can come up with a very nice structure, but there is no way for you to mold it or create weld line in it, which is going to make a structural failure, then none of these things are going to work out. So the problem involved sophisticated kinematics and dynamics of the mechanism, finite element modeling to make sure structurally it's sound, all kind of mold flow simulations and mold parting line and surface design simulations, right? So basically, you can think about it the following way. So you start with the requirements, you come up with the mechanism concept, which basically gives you a stick dot diagram of how the mechanism is going to work. Then you feed that concept into mechanism structure, synthesis, and optimization. It basically is trying to take one of your sticks and add some features to it or reorient a feature to it, shape feature to it. Right? And then you run 4 simulations. So you're doing structural analysis, which is telling what kind of stress, strains, displacement are happening in structure. You run kinematics and dynamic analysis, which are telling you what different forces are resulting. And remember, one simulation result is feeding into the other. You do mold flow simulation to make sure that this whole thing will fill, weld lines are not going to form at the wrong places. And then you do molding cost estimation to make sure that molding will be feasible. Because if you can create this complicated structure and you cannot pop out of the mold, then whole purpose defeated. This is not going to work out, right? So after doing all of it, and this is a simpler version of the problem. So the simpler version of the problem, which we solve it using multi-piece molding. So in the end, you create this, I forget, 1 gram or so, this little plastic part that you create basically, right? With a lot of complicated features here and there, right? So that's part you create. And this becomes your drive mechanism. This is a compliant drive mechanism. You put a gear and a motor in it, and you attach wing, and you spin the motor, and it flaps your wings basically, right? And this is the lightest possible, and if you try to, of course, my students were always saying, yeah, can we go a little bit smaller, shave off another 1/10 of a gram? But then this thing kind of fails, right? So using this platform, we created basically a little bird, which we call a small bird. That's 9.7 grams, can take, I think, 5.7 grams as a payload. And yeah, and it flies at about 4.4 meters per second, and flapping frequency is about 12.1 hertz, right? Then our Army sponsor came and said, hey, this is good, but 5.7 gram, not much payload. There's not much we can put on it, right? So not that useful platform. Basically, make it a little bit bigger so that we can put something, at least a camera on it, so that we can do something useful with it.
Well, it's 50%, right?
Pardon?
Is it scale?
Yeah.
Does it scale? That's...
Yeah, I'll show you. So then we created another version of it, right, which we call Big Bird. So in that case, the payload capacity bumped to 19.1 grams. And this one also can fly up to 6 miles per hour wind outside. So now you can have outside flight with this thing, right? This was good, and we fly this platform with a tiny camera, and I'll show you videos in the end of the section. So you can put a tiny video camera and you can, fly it around, but it's still, the problem is, once you put a battery and a camera on it, you cannot fly this platform with basically some kind of GPS-based navigation where you want to put an autopilot on it and just tell it that go over to Cathedral of Learning and make 3 turns around it and come back. So you can't do that with that platform because doing it in a vision-based thing is going to be hard. So they said, create a platform which can actually have a little bit more, capacity. So then we have to think about it, multi-material molding. So we said, if we do multi-material molding, where we're going to do in-mold assembly instead of creating this single monolithic, advanced polymer composite, but a single thing. So then we can actually do better. But then the synthesis problem gets, much harder. So now what happens is that you have to basically design these very tiny hinges of a compliant material, and the structure, which is going to be rigid polymer, and you're going to mix the 2 things together, and you're going to do the now hinge, optimization and synthesis problem, and the mechanism synthesis problem. And it's a multi-shot molding process, right? So that's what happens in that case. So first you do the mechanism synthesis problem, which is roughly similar to the one which you have seen, or I just talked about before, where you do dynamics, kinematics and dynamics and finite element stuff. And then you feed that into hinge synthesis problem, And these joints sit very tiny hinges, very, very tiny hinges made out of compliant material, right? Which is going to cause local bending, right? Because the problem with the previous design is that you have distributed compliance, the whole thing bends. And the moment bigger version of these birds exert a lot of forces. So if the whole thing starts bending, your idea simply doesn't work. That's why we had to kind of shift to this version. So you do that. And then in this case, it turns out it's a multi-material molding problem. So runner design becomes very complicated problem because this tiny thing is sitting in the mold, and if you inject it with a polymer, and the two polymers which are coming from two sides don't meet at the right time, this thing gets basically pushed to the side, which causes all sorts of problems. So then you have to basically synthesize a runner which is going to get all the timings right so that this thing is going to survive, basically, right? Now, unfortunately, for in-mold assembly, there are not that many good runner design tools out there. So we had to kind of build our own runner synthesis tool in order for us to work on this problem. So we did that. And in this case, you can see this very complicated runner systems get attached to this little tiny frame. So this is a tiny frame, and you see this big, giant runner system around it to make sure that all the timings are going to be right, nothing is going to freeze, weld lines are not going to form in any bad location. So you do all that. And then this just shows you the multi-material molding process. So what happens in this case is that you first mold these tiny hinges, you transfer them in another mold, and you shoot on top of it where you create this big frame, and then when the frame comes out, these hinges are already in place. So that's how this whole process kind of works out. And using which then we created basically a platform which my student called Jumbo Bird, because they thought that after Big Bird the project will die. So then we created a platform called Jumbo Bird, which has now payload capacity of 33 grams. So you can actually put so we are able to nearly lift its own body weight, basically, right? So in which you can put battery, camera, and if you can find a small enough autopilot, which I believe they're out there, but they're very expensive, so we have not flown that with autopilot yet. And I'll tell you some other stories about these birds in a minute. So this actually can fly outside in 10 to 15 miles per hour wind. So now I can show you a few videos of these birds. So this is our small bird. So this is our indoor stadium where we are basically flying this little thing, right? So you can fly it indoor. And if it is not windy outside, then you can basically go outside, and I'm just going to keep advancing it till it gets to the outdoor. So yeah, you can fly it outdoor too if it's not windy. But as you can see, this tiny little thing, it's already, you can see it with a little bit wind kind of blowing it off, right? These things are super light.
What kind of batteries on?
The polymer lithium batteries, a few grams of that, basically. Show you just very quickly how the big bird looks compared to that. But this is what, actually, this is the camera on the big bird, which we fly it with the cheapest possible camera on market, because we do crash these things quite a bit. So, actually, that's not what I meant to show you, actually. Oh, oops, sorry. Keep clicking on the wrong video. So this one you would be able to see when we take it outside, that this flies reasonably well outside. So this is a big bird, which is a medium platform. It flies quite well, it's stable up to 6 miles per hour, and does reasonably well. And then a lot of other birds get startled white, basically. That happens all the time. So you can see that right now, right? And actually, it has been attacked in flight by Falcon. So that's the reason why we don't want to fly it with the expensive camera, because I don't want to be losing cameras. So.
Does it gracefully land when it runs out of battery, or?
No. This is all remote controlled, right? So you have to land it basically, right? So I mean, my students are able to land it within 1 meter by 1 meter target area. But that is with practice. So if I flew it, I'm not quite sure how big that. And this is just for comparison. The jumbo bird, which is. So this is now very stable platform, flies, if you cut down the frequency, it flies very slow. So now you're seeing that we are not having to fly it in a stadium. We are able to actually fly it in an armory, which, and we are going very close to the features. The students are no longer that afraid, basically, right? And this is just flying outdoor. So our army sponsors had seen us launching these by hand. They said, this is a completely useless thing. You guys launch it by hand. If you're going to do surveillance with using these birds, who's going to be there to launch these things, right? So can you integrate UGV versus these bird integration, right? So then we got a couple of undergraduates to basically, so they gave us this little platform which they had built. So now the idea is that you mount this bird on these platforms, basically launch it wherever you feel like launching it, right? So now that you see they are getting more and more aggressive. They are trying to get me in trouble by flying it very close to the campus buildings, basically, right?
So you have to get it up to speed during the launching?
Yeah, a little bit of speed, right. So you have to get a little bit of speed. And then you just hit the brake and then it just takes off. Because it's just mounted with no retainer on the back, right? So the moment you hit the brake, this just takes off, basically. So, yeah, go ahead.
The pitching motion of the flight is controlled by the tail or by the wings itself?
Which motion?
The pitching motion.
So height control right now, so there are two options that you can do, right? So we have a version on which the tail can control it. But all the flights that you are seeing, that they disable that. Because the problem is that unless a very experienced person is flying it, if they just make a little mistake, this thing goes down, very rapidly. So we disable it and we control the climb rate by adjusting the frequency, basically, right? And we steer it by moving the tail, right? So you can, we have that capability, but we just disable it. Not to, every time this thing crashes, then you have to, get new electronics, new motors, so, So that's what happened. So this is the second project. So in this case, basically what we have looked at is now synthesis of mechanical structure, where you're going to look at complicated problem where your structural requirement, your kinematic requirements, your molding requirements, all coming together, and you're synthesizing that shape and then integrate into platform and get them to fly. So that's what basically we have done. And this image is showing you a size comparison of those three platforms. Now, let me just take 5 minutes to tell about this third case study. So third case study, this is funded by NIST and National Science Foundation CPS program. So here the idea is that we are interested in designing a planner which can do basically planning for optical tweezer-based micromanipulation, right? So you can use optical tweezers to pick up very small particles and you move them around. And all of this happens in a fluidic media. So there's a lot of Brownian motion which is going around. And when you have these traps that you create, basically they attract a lot of things surrounding as well. So the problem becomes, we said we're going to use stochastic dynamic programming to do the path planning for it. But the challenge is that you need to really understand what is the probability that if you're going to go by a particle, it's going to be dragged into it. What is the probability that when you start moving, you're going to lose a particle? Because of all of this so you have to do very detailed calculation of rays which are interacting with these particles and what kind of forces they generate and the effect of Brownian motion, and as you're dragging through the fluid, what's going on. So that's what the idea is, and in this case, so I'm going to go through it really fast. So idea is that you are over here and you want to go over there. So how do you go? And remember, all these things are kind of moving around. But optical trap, you can split in the space, and actually not only you can hold on to the thing that you're moving, but you can also make any other thing stationary in the scene. So you can create up to 100 traps in the scene. So that's the beauty of it, but anytime you split, you lose power. So you have to go slow, because otherwise Brownian motion will kick the particle out of the trap. So there are all those complicated trade-offs, and this is a real-time operation, meaning that you have 20 millisecond window to plan your next move. That's it. So whatever you do, you fit in within 20 millisecond window. So you have to do right level of representation, because if you create a grid-based representation which is too sparse, you get lousy plans. If it is too dense, you don't meet your 20 millisecond window, basically, because the stochastic dynamic programming is taking too long time. So in this case, we have done all sorts of physics-based simulation to understand what is the trapping probability of a moving laser beam when it moves near these particles, right? I mean, as a function of particle size, as a function of laser power, laser velocity, all of those things, right? And then you use all of it to compute your transition probabilities when you do stochastic dynamic programming, right? And also tune your workspace, basically, right? So that's what happens a lot in this case. So I'm going to skip through it in the interest of time. So we have built these nice path planners which can actually do these things, both the single particle planning and multi-particle planning. And our interest basically in this case is cell manipulation. So what we are aiming towards is that we want to, and this problem might be of interest to Matt as well, because it's a similar flavor to what you guys are looking into, that you want to grab a cell with a certain number of beads. So the question is, how many beads you're going to use to grab the cell? Because you don't want to trap the cell with optical tweezer, because that tends to kill the cell. So what you do is that you want to grab these glass beads, which are handles, and then you basically grab the cell using this ensemble of glass beads, right? And then you move it around. So then we are trying to answer the similar kind of questions using the simulation-based framework, which includes all this complicated physics, basically, right? So if I put this arrangement of bead, how stable is it? I mean, how fast can I move it? If I use this other configuration, what's going on? How many beads? What configuration? So we're trying to answer many of those questions using the same framework that I just described. So in this particular case, once again, we have demonstrated that you can use these numerically intensive simulation and simplify, do order reduction and meta modeling, and incorporate them in a planning, and then get the planning done. And we have been doing computational synthesis of heat exchangers made out of plastics. We have been doing some synthesis of basically some structures which are created using in-mode assembly. So we play with the computational synthesis in many different application areas. So to conclude overall, the high-speed, high-accuracy simulations are beginning to play an important role in the synthesis process. So using this, you can actually synthesize now things which are fairly sophisticated in nature. And I showed you 3 examples of this blocking policy, of this drive mechanism, and this path planner that we built for optical tweezers. There are many challenging problems. So what happens is that we do, even though meta modeling or all these things, but we do it based upon the context. So then another question is, what general lessons can you learn from it, right? The overall advancing the field of meta modeling or model reduction and so on and so forth. So there are many challenging problems that need to be solved. And humans will continue to play an important role in this overall process. So, I mean, they were the one who will basically be defining the design problem to be solved and also designing the design tool. So a computer just does a lot of grunt work, which most humans find it kind of tedious to do. I mean, accounting for every possible condition and put it in this run the simulation. And there are lots of other applications for the same paradigm. So, you could, where people have decent simulator, but again, physics-based simulator, drug design, intelligent buildings, transportation systems, smart electric grids, where the same idea of synthesizing something complex, not easily decomposable, and then having to really need a simulation to evaluate it, it's also there. So I'm going to conclude with that. Thank you for your time.
Does anyone have any questions?
Yep.
So most, I'm going to use the word optimizers,
Right.
since I think that's fundamental what's going on here. Don't try to understand the thing you're optimizing.
Right.
And I'm going to assert
Right.
that when humans twiddle things to
Right.
make them better,
Right.
they have at least primitive models of what causes what. And they use those models to reason
Right.
rather than just sample and interpolate.
Right.
Are we going to get to that point with these kinds of processes?
Yeah, I mean, so if you look at it, so that's what I want to make a distinction between optimizers and, basically when you're trying to do synthesis, right? So basically, that's the point I was trying to make with the bullet number 1. So you really need to have reasoning technique embedded in there. So what happens that you synthesize something, it fails. So you try to reason that why did it fail? What missing feature did it have? And then you try to add that particular feature.
Okay, so reasoning is about feature selection.
Right. So what caused it to fail and what feature can you put it in there? And then you go back to synthesis to try to synthesize it, right?
Okay. Can you give us an example of reasoning?
So example of the reasoning in this particular case would be, let's say you were working on a problem where, let's say you tried out a rectangular post in, let's say, that mechanism structure you had.
Right.
And rectangular post was causing a locking inside the mold and you couldn't eject it.
Right.
So then you're going to reason that this rectangular thing is not going to work and hence I need to change the shape to a triangular perhaps, right?
Not to monopolize the discussion,
Right.
but
Right.
to me that sounds like I have a shape library of things to try.
Right, right.
And I'm just doing combinatorial optimization of try 1, try 2, try 3.
I mean,
I didn't say, wow, this thing's getting too hot, it's melty.
right.
I need something that doesn't melt at this temperature or something. Some physical
Right.
reason.
I mean, that could be done as well. In this particular case, I mean, none of those examples we're trying to do that inferential reasoning, but it could be done in the framework, right? I mean, none of the 3 examples in which we basically went about it, I mean, most of the reasoning was restricted to what the missing feature is or where the tweaking needs to take place, right? Because the problem happens otherwise is that if it's a complex structure, you don't know where to focus your energy of tweaking things, right? You can keep tweaking things at the random places, which is not going to help you at all, right? But that was the nature of these kind of problems that we were looking into it, right? But certainly more sophisticated reasoners can be integrated, which could then, maybe go beyond. So one could say, okay, what kind of shape should I synthesize which can actually solve that problem, right? So in that case, you could pose the problem in a different way and try to look for a shape which may not be in your library, right?
Well, in this boat thing, it should eventually figure out I need bigger guns.
Sure. Sure. I mean, if that's what, ultimately is within the parameter of what the problems that have been given to you, sure. Sure. Yeah, go ahead.
So I was kind of wondering about your genetic programming approach. So
Right.
you said that you had kind of the human-coded intruder mode.
Right.
And then the genetic program evolved to stop that program.
Right, right.
And I was wondering if it was possible to use a co-evolutionary approach where the intruder and the blocker are co-evolving.
Right, we have tried that. And so we initially tried co-evolution from basically scratch. So the idea was that we're going to seed a very simplistic intruder and we will synthesize a USSV. Then we will basically use that USSV to synthesize intruders, and use that intruder to synthesize USSV, go back and forth, right? So what was happening is that solutions that were emerging were looking very good. However, when you played against human players, so when you didn't play them against each other, when you played with the human players, it turning out the performance was not very good. And the reason for that was that when you are just ranking against each other, you're just learning to exploit each other's basically kind of deficiencies, right? So in a true sense, we were not really creating something which in the end is going to be human competitive, right? Because ultimately, one of the fears is that you want it. Now, other people have looked into that problem, how to make the things human competitive by injecting human input at certain places and so on and so forth. Those are the kind of things that we would like to try. However, there are problems of loss of knowledge in co-evolution. There are stability issues. So many of those issues needed to be, need to be looked at. And yes, then we can go ahead and re-examine that issue. But one of the things that we wanted to make sure that be able to come back and say this is whatever we synthesize is going to perform against a set of humans as well, right? So that became a challenge for us. And that's the reason why we decided for now to stick on a human competitive intruder, which we know is encoding the human behaviors. So when we synthesize something, there's a chances are very high that this will do well against human players. But yes, that's a good point, and we have tried it, and that's something that we would like to go back to it, because writing intruder code is also takes time. So that's certainly something that we would like to
Right. It seems to me the difficulty with injecting the human in there is that he's going to perform so much better than all the other members of the population. They're just going to converge right there.
Right.
So I see.
Right. So that's what the challenges were. That's the reason why we haven't yet kind of found a viable path just using kind of co-evolution, right? But that's something that we definitely have to revisit that approach, basically.
Take one more question. Okay.
All right.
Well, thank you very much, SK.
Thank you.